everybody. Welcome to this kickoff for Mastering the Basic Math Facts, our multiplication and division section. We thank you for being a part of this professional development. We have offered this before, and we hope that this revised edition is a little bit even more smooth than the first and previous versions have been. Our feedback in the past has been very positive. And we hope that you will have a very similar experience. If you have any concerns along the way, I know with an online professional development, sometimes you just need to be able to reach out to somebody and ask a good question. You can certainly email me. My email is just michael.elder@onslow.k12.nc.us. Give me a call. My extension is 20264, or just send a note through Edmodo, and we'll be glad to get together and figure out if there's something I can do to help you as we work through this process. So this is our general format for our video sessions. You'll see kind of a PowerPoint. Today we don't use the document camera at all, but in every other session, I believe from here on out, you will see the document camera being used. And so we'll be looking at examples of tasks to do with kids. But in this first overview session, this is really more about the mindset of mastering the basic math facts. So I'll just lay out kind of where I come from in this. Having taught 4th and 5th grade and worked with kids from kindergarten through 12th grade now, we know that there are kids that just pick up on their math facts, whether they be addition, subtraction, multiplication, division, and then there are kids who struggle. And most kids are probably somewhere in that continuum from I get it right away to it takes me a long time. What we also find, though, is that some of those kids who get it right away don't really get it. They may be able to memorize quickly, but they don't necessarily understand where the facts come from. And then they hit algebra or math 1 and those courses in high school, and some of the things that they thought they knew start to fall apart. So we want to try to help those kids who are struggling, as well as make sure that kids all along the way have a good conceptual understanding. So you see here on your screen, the text that we use is Mastering the Basic Math Facts. And this is a text that we chose because it has a number of really solid strategies. Some you will have seen in other places, some that you have certainly used, and you will add to this resource because you've used a number of things yourself. So I'll share some stories along the way, but in the meantime, let's just go ahead and jump in here and take a look at mastering the basic math facts and what do we really mean by that. So traditionally, and I was certainly guilty of this until I learned a little bit better about how kids learned their math facts, traditionally it's been easy to say, well, let's start with 0 and let's work our way up to 10. Well, what we find is that doesn't necessarily work for most kids, and it doesn't leverage the strategies that we like to use. So we're going to be going at these in a little different order than maybe traditionally is proposed. We hope that you'll be open to that and that you'll see along the way why we begin with our 2s and build up to eventually ending with our 7s. So we'll take a look at those. You will find, I believe, that this is all very strategy-based. So one strategy will lead into another, which leads into another, and that ultimately become a coherent set of things that our kids can use, not just while they're with us in elementary school, but as they move into middle school and into high school. So we're going to stay away from tricks. We believe that, generally speaking, most tricks fade away over time, and that really a lot of times tricks end up using more mental capacity than they save. So we are going to focus on facts from 0 to 10, just not in that necessarily in that order. Some folks will add in 11s and 12s, and that's certainly fine, and it's great to use what we know about 10 to know our 20s and those kind of things. But for the sake of this professional development and the resource that we're using, we're going to focus just on 0 through 10. One of the questions you have to ask yourself, and we each have our own answer to this, is what is mastery? What does mastery of our math facts look like? And so perhaps you're thinking, well, it means I know my facts really, really quickly. Perhaps you're thinking it means that I don't have to use really any mental energy to know them. They're just automatic. I've got them. I know them. It doesn't take me any time with that. we're going to work through using different strategies, as I mentioned, and I hope that over time your definition of mastery may evolve. It may already be where it needs to be, but I challenge you as we go through this to really think about, what do we really mean by mastering basic math facts? We know that there are benefits to us and to our kids. We know that we want kids to know their math facts. We know that very few other things will help them later in their mathematics career, and really just in life, than knowing their basic math facts. We know that when it comes to factoring a quadratic in high school, that you've got to know that there are different ways to make 24, that 24 comes because of 1 times 24 and 2 times 12 and 3 times 8 and 6 times 4, and the more fluent you are with that, the better. Now, how you get to that point is really the purpose of this professional development. So we want people to be really quick and fluent with their facts. That's not, well, we're not negotiating that out. We're certainly not saying that's not important. But what we are saying is that different kids are going to use different strategies to get there. And that we all need lots of experience if we're going to become really fluent, really quick, and really fluid with the way that we think about our math facts. Why do we do that? Well, we know we've got to be able to generalize. So if I forget, well, how do I make 24? I can think of that in terms of, well, I could break it into 2 groups. Well, those would be 2 groups of 12. So 2 times 12 must be 24. We know that we can generalize rules like that. We know that understanding certain strategies will apply across the board. We know then in turn that reduces the drain on working memory, and those of all of you and anyone who's ever worked with kids know that if you get really bogged down trying to remember your facts, you forget where you were in a problem, right? You forget, what was I trying to solve in this problem? So and even just in a naked number problem, if I'm just doing a division problem, kids will forget where they are, right? We've seen that, and we see it time and time again. If they're struggling with trying to remember what the math fact is that's going to help them answer that question. So we know that we want kids to remember their math facts, to be fluent with them, so that they can generalize the rules, so they aren't taxing their working memory quite as much, and ultimately so they can determine if an answer is reasonable, and that, does this estimate make sense? If I round these 2 things off, does that give me kind of a close answer? And is a close answer good enough? So those are really our 3 primary reasons that we focus on kids knowing their math facts, even more so than that we know it's going to matter to them later. So when we look at resources, you or your school will receive a copy of the text that we're using here, and we'll ask them to put that in your school's professional library. We'd love to give one to everybody. Unfortunately, financially, that becomes a little bit of a strain. So we'll provide one to each school. Really, you only need the text once, because everything in the text is on a CD. We'll be posting the ones that we use here in our Edmodo group. You can pull those down. You can use them to help you if you're going to find them useful for yourself, or if that's just one of the tasks we're going to use. So once you have their copy of the text, you get a code, and you can go to the Heinemann website and download the resources from there. Like I say, we'll also post them in Edmodo for while you're in this course. Like I said, we'll be sending a copy of the text to your school for the professional library, so you can go and grab it, make your copies out of there that you want. For pre-assessment, there's a good table in our text that we'll share in our next session, because it's really important to understand or to know where our kids are as we start. We know that some kids are going to come into 3rd grade, if you're a 3rd grade teacher, knowing some of their facts, and really understanding them and having a deep conceptual understanding of them. They may know them all, they may know some, so we need to make sure that as we're working with kids that we're not just starting them all in the exact same place. That doesn't mean we can't do the same mini lesson with all the kids, because sometimes it's good just to go back and touch on, what are the strategies for 3s, and what are the strategies for 6s. That's good for us all as we work through these things, but it's probably not a best practice to have all kids working on the same math fact at the same time. So we're going to assess what do kids already know. We're going to assess what are they automatic with, what are they really quickly fluent with, and then do they have a deep understanding of those facts as well. So we go back to that idea of what does mastery really mean, because if I'm not really sure what I believe mastery is, then I might be asking kids to do something that's really above and beyond what they need to be able to do, or I might be cutting them short. So all those pieces come into play, and all of that can be looked at through pre-assessment, and pre-assessment can be anything from a written test to asking kids questions. Oftentimes asking them questions will get us more than anything else. So we'll be looking at all kinds of resources for that throughout this professional development, so we won't get bogged down in that here. This professional development is broken up into 13 sessions. Some are longer than others. This overview session is the first one, and then we move into the facts in the order that you see here. So we go through multiplying by 2s, then 10s, and 5s, and 1s, and 0s, and 3s, and 4s, and 6s, and 8s, and 9s, and then finally 8s and 7s, and then we wrap up. We do need to wrap up this professional development on time. However, some of you will move through it at different rates. So you will find that I generally post these about once a week. Every now and then I might post 2 or 3 of them at once and say, look, if you want to do them all at once, you can do that. I know that any one of our schedules is not always ever the same from one week to the next. So generally speaking, we'll post these 1 per week, and that'll get us wrapped up in plenty of time to turn in for our credits for this semester. We've already mentioned this, so I'll dwell on it here. We won't be going in numerical order. We'll be going in the order that you saw on the previous slide. The pace of this professional development is one that sometimes fits what you're teaching in class, and sometimes it doesn't. Some of you might be taking this simply to add to your own skill set, and you may not have any students to work with. So at different times we'll ask you to try an activity with a student. Generally, you can find whether it's a student you're working with or whether it's a family member. We've certainly done that to our own family members, a neighbor. And if it really comes down to it and you can't find anybody, sometimes we just act and we pretend and we work through the task and see, well, how would a 9-year-old really think through this? So I'll be very flexible on this side of things. I'll trust your professional judgment to use these things in ways that make sense. Another factor that comes into play is if you're doing this at the beginning of the year, it kind of fits. If you're doing it at the end of the year, you might say, well, I've already done a lot of this, so I'm just going to add this to what I'll do for next year. So I totally get that, and we want to be flexible with you on that and make that make sense for you in the way that it'll fit your professional learning too. We do ask you, or I'll ask you throughout this, to share your professional experience. It's always easy to get bogged down in a particular student, so at times we'll ask you to think about in general, and then sometimes we might ask you to think about a particular struggling student or a student that really excelled. So we just ask you to share those experiences. This hopefully is a safe professional learning environment, and that you'll be willing to share those things because we all benefit when we hear from one another. Mastery, as we've kicked around already here today, there are ideas about automaticity, there are ideas about understanding. Generally, when we talk about something being automatic, when you think about what can I do automatically, what are the words that just come to me when I want to speak? What are the actions that I do automatically when I get out of bed in the morning, when I brush my teeth? The things I don't have to think about. Automaticity is that same idea, right? The ability to effortlessly recall a fact, right? The ability to just know it, that 4 times 3 is 12, and I can say that and move right into the next thing. That would be some level of automaticity, right? But it's not grounded in memorization. Memorization is a whole different mental strategy, right? You think about all the things you've memorized in your life for a test, and then quickly after the test, it fades. So sometimes we talk about memorization, and what we mean is automaticity. And I hope throughout this professional development that you really get that we refine our language a little bit. There is this idea that students who memorize are smarter than kids that don't. And we know that's not true in the long run. We know that we've got, just in the same way that in language arts we talk about, we've got kids who word call and don't understand. In mathematics, we can have kids that number call and don't understand. So they may say 4 times 3 is 12, and they may kind of have that. And if we're doing fact of the week kind of things, they may be able to give it to me on Friday, and then 2 weeks later you ask them what 4 times 3 is, and they have no strategy for it. They don't know, and they don't understand. And I know we've all lived that reality, but we need to be careful that we're talking about automaticity towards mastery and not memorization. The next few slides here are courtesy, and you can pull any of these resources from NCDPI, and I thank them for doing this. The webinar they did several years ago, which was really focused on automaticity over memorization, and that we hear in the public, I want my kids to memorize their facts. And we say, well, I'm not sure you really want them to memorize them. I think you want them to be automatic with their facts. I think you want them, and to some degree that might be semantics, but I think there's also a level of misunderstanding in terms of what we really want kids to do in mathematics. So I want to make sure I give credit to Kitty Rutherford and their team at DPI who developed the webinar that you see at the bottom of the screen here, and the links that you see on the slide here take you to the games that they've created. These are all in the Math Wiki space for our DPI. So pull those down, use them. They are great resources. We've tried not to duplicate those in this professional development because we know that a lot of folks are already using those. But if you aren't, that's another great resource to go and pull from. So let's just delve into this a little bit about what does it mean to have computational fluency. And again, these slides are all directly from our friends at DPI. So you look at the keywords here, right? Like the computational fluency is efficient and it's accurate. We've certainly seen kids who are very efficient. They quickly come up with an answer, but it's not necessarily the right answer. And sometimes those are the knocks we hear on whether it be a silly Facebook post or somewhere else, that all answers are okay. And we know that's not the truth. We're not advocating that all answers are equal, but we are going to advocate that kids who use a good strategy, they may come up with a wrong answer. Doesn't mean we honor the answer, but we might honor the process that they got there. But if I'm going to be fluent, that means I have efficiency and accuracy, right? And that because I've built a because I built a conceptual understanding, I can be flexible in how I use numbers, right? That I can take any number, I can take 36 and figure out how many different ways could I break that into its factors. What are the multiples that will get me 36? But that I can do all that very quickly and efficiently. All of that being grounded on what a student really understands. Because if they don't understand it, they really can't apply it. And if I can't apply it, then it's simply a fleeting thought, right? It might last me for a week, it might last me until an end of grade test, but then the next year we're back and we're reteaching it again. So we're going to teach things that are grounded in the base 10 system, because that's our number system, right? They're going to be grounded in the properties of multiplication, and they're going to be grounded in that numbers and the relationships between numbers matter, and that by knowing certain things about one number, I can use that to help me with another number. We want to make sure that when we're talking about fluency, it's not just 7 times 4, right? But that it's understanding that we're talking about 7 groups of 4 or 4 groups of 7, and those two things are similar in value, or they might have the same value, but they're very different representations, right? Like if I think of 7 rows of 4, that's different than 4 rows of 7. That's a different configuration. 7 groups of 4 sheep is different than 4 groups of 7 sheep. It might have the same value, but there's a very different configuration going on there, and that matters later on in our math. So we need to embed what we do in problem solving, And then at times we're going to pull it out so we can really just focus in on those facts. So that begs the question, okay, so we've talked a lot about this is needed. We can all agree that it's needed, but I was talking to somebody recently and they said, well, come on, isn't it really just about recall? And I don't think it really is just about recall. It's about understanding. And recall is certainly a part of that, but it's not the whole part. And I think that many of our friends who aren't involved in mathematics, that recall and memorization, that may be what they think math is all about, but that's not really what math is about at all, right? Math is about being able to apply what we know and solve problems. So we've got to have a balance, and we've got to make the connection between the concepts and the computation. So there's nothing wrong with practicing our math facts. We're going to do that, but we're going to do it in a meaningful way, and we're going to use it in game situations. We're going to put it in relevant problems, because we know, and NCTM and their principles and standards points out to us that you can practice and practice and practice and practice, but that doesn't mean you're going to remember. And it can actually hurt your ability to be able to problem solve in the long run. So we've got to balance those two pieces together. We've got to present problems in known situations as well as novel situations. And we've got to understand that the expectations grow over time. And not all kids are going to hit the same expectations at the same point. But generally in the Common Core standards, or even before we had the Common Core standards, this is pretty close to about what we were asking kids to be able to do. So looking at what are kids expected to know and be able to do in kindergarten through 6th grade. And so you can look at this, kind of pick up where does my grade fall in here? What am I asking kids to do? And so obviously this doesn't mean that any of these things go away. So you see in 3rd grade, multiply and divide within 100. And then in 4th grade, add and subtract within 1,000,000. That doesn't mean that multiplication and division have gone away. It means that we might be moving from models to without models. So we have to go back and look very carefully at our standards and see what are we expected to do. But we do see that by 5th grade especially, our kids are really expected to apply their knowledge of math facts. We know there are going to be kids who are still working on mastering their math facts moving into 5th grade. Kids are going to develop at different rates, and we all live that every day. So as you work through this, be thinking about, well, it may not be about what grade they're in, but about where are they on this progression, and keeping track of where kids are on this progression, and making sure that if I'm the 4th grade teacher, I'm communicating to the 5th grade, these are my kids who really have it nailed. These are the kids you're going to still need to work with. I think that communication piece is incredibly important. At times when we're talking about multiplication facts, the idea or the topic of algorithmic answering, or using the standard algorithm, saying that if I have 14 times 7, there's only one way to do that, and that you have to multiply 7 times 4, and that gives me 28, and I put the little 2 on the top, and I take the 7 times the 1, which isn't really a 1, but it's a 10, and then I say that's 7, and I add 2 more, even though that's 20 more, and I write down a 9 because that's 90, but I write down 9 because it fits in the little box, and I have my answer. That's the algorithm, right? But it isn't necessarily what makes sense to kids, and it isn't the progression that we're asked to deliver. It is where we want our kids to end up, but based upon a deep level of understanding. So in the same way that we're learning our math facts, we're learning how to use our math facts in a conceptual way. So sometimes that begs the question because, well, it begs the question for a number of reasons, but it begs the question of, why don't we just teach the algorithm? Come on, Michael, it's so much easier if I just teach the algorithm. Well, the algorithm is meant to be efficient and effective, right? But it also is meant to be the end product, not the initial part. So Common Core state standards and principles and standards for math before that talks to us about our computation strategies as well as our algorithms, right? So there are strategies, right, that may or may not have a fixed order that you could do. Again, if I had 2 digits times 1 digit and I had 14 times 7, there's no reason I couldn't say 7 times 4 is 28, and 7 times 1 is, or 7 times 10 is 70, and 70 plus 28 is 98. And I might be able to hold that in my head in a much more meaningful way than I could just trying to hold the algorithm in my head. So we think about, there are times that it really is actually more efficient to use the strategy than it is to use the algorithm, and that the strategy is really based in base 10, and the order may not be nearly as important, because again, I could have done 7 times the 10 first and got 70, and then added on 7 times 4 is 28, if that was easier for me too. So I've got to go here, right? So this is, does it work? So Michael, this is all great, and I hear what you're saying, but does it work? So I will tell you, this is a little dated. It has been repeated. This is Kathy Kami, I believe. And what she was looking at was, okay, so if we give kids the algorithm and we see how they do with this question of, this is an addition statement, but we're going to extrapolate it to multiplication. If we said, okay, 7 plus 52 plus 186, let's just use those 3 numbers, and that problem is right here. And this was given to 3 classes of second graders, right? And so in one class, this first class, this teacher had taught purely the algorithm. So the only thing those kids got was the traditional line them up, add the 7 to the 2 to the 6, carry, and that whole piece. We know the algorithm, right? And what she found was that 245, which is the correct answer, that 12% of kids in that class, and generally, by the way, balanced across the board in terms of ability going into this task, but about 12% of those kids got it right. So you can see a bunch of kids got these answers, a bunch of kids got, or some kids got these answers, and you can see they're all over the place, right? And it'd be fun to break them all down and decide, well, how did they get those? But for the sake of the time that we have, that was the group, that was given algorithms, and that was pretty much it. The second group had some algorithms, and that they had kind of been taught at home. They had a little bit different experience, so they had a couple things they could pull on. They had what they learned at school, but it was still generally algorithmically based. And what they found was, well, when you get that piece of it, we go from 12% up to about 26% of those kids got it right. So you can see their answers, they varied a little bit less, but still only 26% of those kids got it right. Now, if we go to the group, then we go to the third class, right? And so in the third class, they were not taught an algorithm, so they didn't have the general line them up rule. They had strategies. We're going to talk about using our 10s and our 1s. And we can see that the cluster here, right, still 45% of the kids in that group were correct. And if we look at the variance in the answers that those kids came up with, it varied a lot less, right? So we might be tempted, or oftentimes we're tempted to say, but the way I learned must be the way that works. And so I want to go with that. And most of us were taught with an algorithm, or what we remember is the algorithm, and we forgot that people gave us strategies to begin with. So we'll work through some of those ideas, but just interesting data. And again, it's dated, and this is addition, but I think generally speaking, I would tend to agree that if I have some good strategies, I could probably apply those to a variety of situations, not just the one particular situation that I find myself in with this problem. So does it work? I would advocate that it does. I think it takes time, but that's up to all of us individually to figure out. So we're going to focus on sense making, and again, just more references as terms of why not just go to the algorithm? Why not just have them memorize it? And because our focus is going to be on mastery and understanding and building up to that. And it is frustrating building up to it. It's also frustrating whenever we spent years telling kids to memorize them, and every year we're starting back at 2s and 3s and 6s and saying our kids don't know them. So the frustration doesn't go away. I don't want to lead any of us into that idea, but it's a frustration that leads to success instead of a frustration that leads to more frustration. So I think we've hit those ideas already. When we talk about drill, right, so there are entire series out there, right, on math minutes, mad minutes, all those kind of things. And really what we find with those is there's nothing wrong with using them. However, we may want to think about how we use them and how often we use them. Because drill does help strengthen skill, right? Drill builds muscle memory, it builds repetitive memory, but only if I'm really practicing what I know. So if I'm practicing the facts that I own, the ones that make sense to me, that can increase my automaticity, it can increase my speed. Those are the times it's fun to race against one another. But if I'm just trying to remember them for the quiz on Friday or for the math minute on Friday, it's not found to be as helpful. So without some sort of strategy to back it up, drill is not nearly as effective as we might want it to be. Why, again, do we want kids to memorize, right? We talked about this at the beginning. We want them to be able to generalize. So if I know 5 times 3 and then all of a sudden I see 5 times 30, well, I might be able to figure out something about, I might be able to use something I know about 5 times 3 to solve 5 times 30 or to solve 50 times 30. We talked about memory, our working memory, and we can think about all kinds of skills that we have, from driving a car to operating a computer. Think about the first time that you used email or the first time that you used some new app on your phone. It's a little clunky, right? And then you gradually get more fluent with it. And that happens because we're making sense of the process, not because we're memorizing the process. And we're able to be more reasonable with it. So let's just take this out of math for a minute. And let me give you 2 sentences. And let's think about which is easier to remember. Okay? So you ready? All right, so here's our first sentence. Sat, chair, red girl, a in little the or. Got it? Or would you rather it say, a little girl sat in the red chair? Same words, right? Same words, different arrangement. I think we ask ourselves then, well, what's the difference? Well, if we're asking kids to memorize without it making sense, it gets incredibly discouraging, right? It gets incredibly frustrating for the kids because I keep trying to remember 7 times 6 and I can't remember, and now I know I don't know, and now I'm just not good at math, and I'm going to find a way out of this, right? So I'm either going to shut down, I'm going to act out, I'm going to just not do it, whatever it is. Kids will start to see 7 times 6, and some of them will just remember 7 times 6 is 42, or we have any of the tricks that we teach kids along the way, and they start to see these things as pairs of numbers instead of things that make sense, right? That if I'm doing 7 times 6, well, if I remember that 7 times 3 is 21, well, 6 is twice 3, so that must be 2 groups of 21, that'd be 42. If I understand how I can use doubles of numbers, that's going to help me throughout, right? Whether I remember all my facts or I have to use some strategies like that. And I think cognitively it's the equivalent of sat, chair, red girl, a in little the for some kids. That's what they're seeing when they see 7 times 6 equals 42. And they just have nothing to connect it to. And so it's this jumbled mess in their head. So when we're looking at this, when we work through the text, when we're working through these, I hope that all the activities push us to think about how we can help students make sense of it. And so they're seeing the sentence that makes sense and not the one that is just jumbled up for them. So we're going to look at these kind of big ideas and these strategies, right? That knowing our operations is a fundamental skill. We're not going to excuse that kids don't know their facts, but we're going to help you through it. We know that kids need hands-on explorations. We know we've got to start with concrete. We're going to move to representing it, and then we're going to eventually hit our abstract. We know we've got to at times embed in real-world problems, and at times we've got to pull it out and say, let's just look at what the fact says. And then finally, and we'll use this with each one of our facts, a connection to literature can make all the difference for some of our kids. So with each of our facts here that we'll do, we'll share a story. Gives me a chance to read a story, and it gives you a chance to add to your repertoire of how do I connect math and the literature, and give kids something they can reach back to and have that, oh, that's right, we read this book when we were learning our 2s or our 5s. So when we look at these, we know there are lots of strategies that kids can use, right? When you're looking at something as simple as 4 times 3, some kids might use a doubling strategy, some kids might use a double and one more strategy, some kids might use a halving strategy. Whatever the strategy is, it's because it makes sense. And finally, we're going to make sure that our kids know and are using the commutative property to cut down the number of facts they have to remember. We're going to use the 0 and 1 properties. We're going to use patterns a lot. And we're going to decompose our numbers. As the instructional leaders, we're going to make sure that we give our kids lots of frequent practice, but not incredibly lengthy practice. So finding that kind of quick hit practice is much more beneficial for us and for our kids. And it's easier to fit into the day and through a variety of activities. And that really, and this one gets a little touchy, and I don't want to offend anybody, but we're not going to focus on who's the fastest, right? That we're not looking at speed as our indicator of greatness. That faster isn't always smarter, and faster isn't always better. We're going to encourage kids to build their own automaticity, but if we're going to do speed, it's going to be, I'm going to compete against my own best, right? I'm going to try to get better than I was last time. So this is the organization of the text. You will find that we're going to focus most of our energy on multiplication, and little bits at the end of each session we'll look at how do we reverse what we've done to focus on division. So using multiplication to understand division is generally what we find works with most of our kids the best. So just clicking through a few of these things because these are things we'll hit in every single chapter. When we look at student work, we're always going to quiz ourselves to think about, well, how does one student solve this, and how would another student solve it? And how would I solve it? So if it's a birthday party and this girl has made a favor bag for the 5 guests at her birthday party, and she put 3 stickers in each bag, and how many are in the bags altogether? Some of us are just looking at that and saying 5 times 3, she put 15 stickers, can I please move on to the next question? Well, that's good, except that we don't all teach kids who are exactly like us, right? So we have to think about, well, what about my struggling kid? What am I going to do for that child here? How would they picture it? Do they have any picture, or are they just trying to guess, am I supposed to add, subtract, multiply, or divide those numbers together? And maybe if we're on the multiplication chapter, I guess I know I'm supposed to multiply. But we see that with our kids all the time. If they're not trying to make sense of the story, if they're not trying to draw it out, then they probably are going to struggle with the answer, right? So just some other types of questions and thinking through, how would you solve it? How would some other kids solve it? So whether it's boxes of crayons and desks, or books on a shelf, thinking about different ways to represent that. And is it drawing it out is certainly a strategy. Are there ways to model it? Who's going to need concrete models? And what do I do if a student just says, well, there's 30 crayons, right? Or there's 48 books. Do I know that they know how to solve it? Or did they just guess and they know their facts, but they don't necessarily know how they got there? So one of the pieces that we'll work through in this text, and that if we don't come back to it every single time, it's really important to think that as we approach each fact, that we're teaching our kids that there are a variety of ways to solve any problem, right? And that we can use an array, right? We can do pictures of the sets of things. We can make it repeated addition. We can make it an area model. So I'm a little limited on space here, but let's just say we were doing, for sake of space here, let's just do 4 times 3, right? So this might be the multiplication fact we're focusing on today. So if I'm doing an array, right, that would be something like, right, I've got my 4 rows, 1, 2, try to make this somewhat equal, sorry. Oops, my line went down a little bit. And I've got 4 rows and I've got 3 columns. So in my array, I can count up that I've got 12, right? Okay. As a picture of sets, right, I might have 4 groups of 3. There's my 1 group of 3. Sorry, I know my drawing is not beautiful on here, but that's never our strength in math, or I shouldn't say never. That's rarely our strength in math, is making this thing beautiful. So I've got my 4 groups of 3, and ideally I would certainly mark those all so that you could see there's 1 group, 2 groups, 3 groups, and 4 groups. And that also happens to be, when we count them all up, 12. For some kids, they're going to say, well, no kidding, it's 4 times 3. It's always going to be 12. And for other kids, they're going to say, well, how is that the same value as that? Those look very different. And based on the situation, they are very different. In an area model, right, we've got our 4 over here. We've got our 3 down here. So this is going to be 4 long. It's going to be 3 wide. And that, again, could look a lot like an array. Sometimes it's marked off, sometimes it's not. And as repeated addition, I can say, well, that's 4 groups of 3. So that is 3 plus 3 plus 3 plus 3. And that, by the way, also happens to be 12. And once again, these all make the same value. They might not look the same, they aren't the same, but they have the same value, and the fact is all 4 times 3. So if I'm working with kids with this, I want to build situations where the array is a good strategy, where the area model is a good strategy, where the sets are a good strategy, and where repeated addition is a good strategy. Area model is going to be much more beneficial when we get into 2 digits times 1 digit and 2 digits times 2 digits. Not quite as clean when we're just doing 1 digit times 1 digit. But if I fail to keep coming back to this, remember that looking at these 4 models of multiplication or division is huge and keenly important to our kids understanding how all this math comes together. So there is the ideal, and then there is the real, right? And we all live in the real world, but sometimes we get to sit back and think about ideally, right? So ideally right now, I'd say, okay, now go give a pre-assessment to all the students you're working with, and let's come back and let's talk about where your kids are, and then let's use these strategies with the kids where it makes sense over the next several weeks. In reality, you are somewhere in your school year already, and you've got to determine what makes sense, because you certainly can't stop kids and say, well, I'm taking this professional development, so you're going to have to do this test for me. So I don't want anybody to do that. But if it makes sense as we work through these things to pull a student, please do that. If the fact happens to be something your kids need to work on, great. If it doesn't, and there's a neighbor you can steal or your own child you can use, that's great. And like I said at the beginning, if those are absolutely out of the question and they're just not an option, and you can't go to somebody on your campus and find a kid that will work, that's fine. Just reflect on what we do. We'll be moving in next week to multiplying by 2. We'll be sharing our story. We'll ask you to share some ideas. So for this overview session, all that I would like you to do, I'll post an assignment. This video will be attached to that assignment. And the assignment will be to just describe how did you learn your multiplication and division facts. And then to reflect on what kind of students do you think that those strategies that you remember, who do you think those would be effective for? And maybe some kids do you think, the way I learned it probably wouldn't work for these kids. So this is more of a personal reflection for this assignment, and I look forward to seeing you in our next session, and I hope that you are doing well, and thank you again for participating with us in this professional development.